Hello everyone. Astronomy has always defined stars by their light. A star, by its very nature, was expected to shine, producing energy through ongoing fusion reactions in its core and radiating that energy as light and heat. This understanding gained universal acceptance, spanning everything from stars far larger than our Sun to those that ended in explosive supernovae. Stars were classified by characteristics like brightness, temperature, mass, and lifespan, and viewed as orderly, predictable components of the sky. But this classification relied on a crucial assumption that nothing invisible was being left out. Dark matter, which makes up most of the universe, neither emits light nor absorbs it, and so it can't be directly observed. Yet indirect clues like the rotation speeds of galaxies and the mass distribution within globular clusters clearly reveal its presence. But what if a star could shine only because of this invisible matter? This idea gave rise to the concept of the dark star, and this concept stretches back to the earliest eras of the universe, to its largest structures, and to the most fundamental laws of physics. So what did the first stars in the universe look like? For many years, the answer to this question was based on speculation. But a recently proposed model has the potential to shake the foundation of everything we know about stars, because some stars may not get their glow from hydrogen fusion, but from the most mysterious substance in the cosmos, dark matter. Dark stars depend entirely on this invisible substance from which they take their name. Dark matter, believed to make up about 85% of all matter in the universe, neither emits nor absorbs light. Therefore, it cannot be directly observed. However, according to some theories, this mysterious form of matter contains weakly interacting massive particles, or WIMPs. As their name suggests, these particles interact with other matter in the universe almost not at all, only through gravity and the weak nuclear force. And under certain conditions, these particles are predicted to annihilate each other, releasing energy in the process. This is precisely where the operating principle of dark stars begins to take shape. In the very early universe, just a few hundred million years after the Big Bang, gas clouds accumulated in regions rich in dark matter, and gravitational collapse set the stage for star formation. During this collapse, WIMPs gathering toward the center increased the likelihood of collisions as density rose. When WIMPs annihilated one another, the resulting energy heated the gas, creating thermal pressure that counteracted the star's own gravity. In other words, these stars began to shine without ever needing nuclear fusion. Traditional stars only begin producing energy through fusion once their core temperatures reach millions of degrees. But in dark stars, internal heat is supplied by WIMP energy, so their core temperature remains much lower, around 10,000 Kelvin. This allows them to exist in a larger, more diffuse, and cooler form. A star that glows without ever igniting, that shines without burning. And this process may have started long before the first stars we can observe ever formed. Having a different energy source changes the entire structure of the star. The central temperature is lower, the diameter is much larger. Even though the mass is high, the surface temperature is relatively low. As a result, it emits mostly in the infrared wavelength. Bright but cool, massive but loosely structured, this is what such a celestial object would be. And because these stars operate not with ordinary matter, but solely with dark matter, they cannot be part of the classical stellar evolution process. They do not become white dwarfs, nor do they go supernova. That's because the fuel that powers them is a type of matter whose depletion doesn't follow conventional processes. As a result, all known scenarios about a star's lifespan, transformation, and death no longer apply to dark stars. In other words, from the way they form to their internal structure and evolutionary path, these stars defy everything we're familiar with. So how big are these stars? Theoretical models suggest that their diameter could exceed 1 billion kilometers. That would make them nearly the size of the entire solar system. They could be large enough to encompass the orbits of Mercury, Venus, Earth, Mars, and even Jupiter. In fact, if a dark star were in the Sun's place, Jupiter would orbit inside it. This enormous size gives them a low-density structure. Despite their immense volume, their mass may be comparable to that of conventional stars, and their light is mostly emitted in the infrared spectrum. So while they may not appear bright in visible light, they actually radiate significant energy due to their large surface area, even at relatively low temperatures. So why hasn't such an enormous star been seen until now? The answer lies not just in their size, but in when and where these stars may have formed. For a long time, dark stars remained confined to theoretical models. That's because their energy production mechanisms fell outside the boundaries of known physical processes. They didn't shine through fusion, nor did they leave detectable electromagnetic signatures. Seeing them would only be possible with a telescope capable of observing the earliest periods of the universe. That technology became available only in 2022. The James Webb Space Telescope was designed specifically to detect infrared light emitted by celestial objects formed just a few 100 million years after the Big Bang. This early era had never been directly observed by any previous telescope. In its first months of operation, the data it returned exceeded all expectations. The telescope detected several distant galaxies that appeared much larger and brighter than their age would suggest. These galaxies conflicted not only with their expected ages, but also with the structural predictions of current evolutionary models. Galaxies of this scale weren't expected to exist so early in the universe. The rapid organization of stars, gas, and gravitational collapses couldn't be explained by any known astrophysical process. As a result, some researchers proposed that these objects might not be galaxies at all, but instead extraordinarily bright individual stars. And these stars largely fit the definition of dark stars. The infrared light they emit falls perfectly within JWST's observational range. In other words, this telescope has opened a uniquely suitable window for detecting dark stars. Among the detected candidates, objects like JDS 13 and Sears 9 3316 stood out. These structures appeared extraordinarily bright for their age and didn't fit into standard galaxy formation scenarios. Spectral analyses showed that these objects did not possess a defined core structure, but instead had a wide and uniform brightness distribution. This raised the possibility that they might be single stars or star-like structures. However, reaching a definitive conclusion will require much longer observation periods, new spectral data, and telescopes with even higher resolution. So is it possible for an ordinary-looking star to display behavior that defies the laws of physics? Tabby's star holds the most intriguing answer to that question. In 2015, while analyzing data collected by the Kepler Space Telescope, astronomers noticed an unexpected pattern in the light curve of what seemed to be a normal star. This discovery wasn't the result of a major institution or an automated algorithm. The first to notice the inconsistencies in the light curve was a group of volunteer citizen scientists. The star's official name was KIC 8462852, but it later came to be known as Tabby's star, inspired by the surname of Tabitha Boyajian, who led the discovery. The star's brightness would suddenly drop at irregular intervals, then return to normal. But these changes were neither consistent nor predictable enough to be explained by known planetary transits. Sometimes the brightness dropped by 1% for just a few hours. Other times, it fell by an extraordinary 22% and stayed that way for days. This behavior was unlike anything ever observed in any other star. Moreover, beyond these temporary dips, a long-term decline in the star's overall brightness was also detected. When old photographic plates were examined, it became clear that the star's total light output had been gradually decreasing over the past 100 years. So there was not only a pattern of short-lived dimming events, but also a slow and permanent fading process taking place. These two different observations led scientists to consider unconventional explanations. The star was not young, and there were no signs of a large planet regularly transiting around it. The brightness changes weren't periodic, they were random. Sometimes weeks passed between events, other times nothing happened for months. In addition, the duration and depth of each dip varied. That meant the star's light curve couldn't be matched to any orbital pattern or explained by a symmetrical model. This behavior raised the possibility that there might be an extraordinary structure around or directly in front of the star. But what this structure is, how it formed, and why it has only been observed in this star remain unclear. There are a few theories that attempt to explain these unusual dimming events. The first possibility that came to mind was the transit of a massive planet orbiting the star. But the amount of dimming was so great that any planet that large would no longer qualify as a planet, it would fall into the category of a brown dwarf. Yet infrared telescopes were unable to detect any such object. No visible structure of that size was present. Another possibility was that a wide dust disk surrounded the star. Young stars sometimes have such formations, but Tabby's star belonged to an older system. Moreover, dust disks emit infrared light. So if that were the case, there should have been an infrared signal in addition to the Kepler data. But no such emission was observed. Later, a swarm of comets orbiting the star was suggested. Perhaps a large number of small objects were blocking the star's light at specific intervals. This scenario could partially explain the short-term dimming events, but the long-term decline in brightness couldn't be accounted for by this model. In addition, the total mass required would be equivalent to several planets. A swarm that dense would be expected to leave lasting effects, but none were observed. And all of these scenarios raised another question. If this is happening, why isn't it observed in other stars along the same line of sight? That question still remains unanswered. A speculative idea that was later proposed edged into the realm of science fiction. Perhaps there was an artificial megastructure built by an advanced civilization surrounding the star. Such a structure could gradually block the star's light, alter its direction, and create a pattern of dimming that was systematic yet unexplainable. This possibility is not treated as a serious option in scientific circles, but rather as a theoretical scenario. In short, every explanation opened the door to a new unknown. None of them could account for all of the star's behaviors at once. But some stars don't just display unexplained behavior, they outright violate universal rules. They can reach such extraordinary speeds that they escape the very systems, even the galaxies they were born in. Galaxies are known for their gravitational coherence. A star can't easily break free from the pull of the system it was born into. Yet some stars clearly defy this rule. They accelerate to such extreme velocities that they are ejected from their galaxies altogether. These stars are called hypervelocity stars. Hypervelocity stars are usually observed moving outward from the center of the Milky Way. Some gain momentum through chaotic interactions near a supermassive black hole. Others are flung into space when their companion in a binary system goes supernova. Each scenario is different, but the result is the same: a velocity strong enough to overcome even galactic gravity. One of the most intriguing examples in this category was a star discovered in 2020, CWISE. Observations revealed that this star was moving at an extraordinary speed of about 1.2 million miles per hour, or roughly 550 kilometers per second. That velocity was high enough for the star to completely escape the gravitational field of the Milky Way galaxy. Even more remarkable was the nature of the star itself. CWISE was classified as a low-mass, metal-poor star. These types of stars are typically found among the older populations of a galaxy. But the direction of this star painted a different picture of its journey. Observations showed that it wasn't moving outward from the galactic center. On the contrary, it was headed toward it. This raised two possibilities. Either the star had been ejected from another galaxy and was being pulled toward the Milky Way's core, or it was under the influence of an entirely different dynamic. So far, only a few dozen hypervelocity stars have been discovered, but now similar stars originating from other galaxies are also being detected. This suggests that they may not just be the result of local events, but rather of processes that operate on a cosmic scale. But in the world of stars, unexplained behavior isn't limited to orbits or velocities. Sometimes it lies hidden within the star's very composition. And some stars don't just behave erratically, they act in ways that are outright illogical. The most striking example of this is Pribilski's star. Astronomically catalogued as HD 101065, this star was studied in the late 1960s by Polish astronomer Antoni Pribilski. What stood out in the spectral analysis was an unusual abundance of elements. But this unusual abundance went beyond typical stellar elements like iron or calcium. The star's light contained uranium, thorium, and even promethium, extremely heavy and radioactive elements. Promethium was especially noteworthy because it has no known stable isotopes. In other words, for it to be observable in the star, it must have formed very recently. The problem is that producing such elements directly within a star is not possible according to known astrophysical processes. Supernova explosions, neutron star collisions, or man-made nuclear reactors, such extreme conditions are typically required for these elements to exist. But Pribilski's star is not a supernova. It's not a neutron star. And what's more, there is no visible remnant or trace of any past event around it. So where are these substances coming from? Could they have fallen onto the star's surface afterward? Maybe a piece of dark matter or the remnant of a neutron star collided with it? Or perhaps the star possesses an entirely unknown element synthesis mechanism? None of these questions have been answered yet, Pribilski's star still stands alone among all stellar classifications. Its chemical makeup, its behavior, and its spectrum have no known counterpart. And perhaps for that reason, scientists continue to debate whether it's truly a natural star or a cosmic anomaly on a universal scale. Astronomy is, more often than not, a science that moves forward with statistics, light curves, orbital calculations, mass luminosity balances. But sometimes a system is observed that defies every model we have. The structure known as the impossible triple is exactly that kind of exception. This system, detected in the Kepler Space Telescope's data archive, appears to consist of 3 stars. But the problem isn't how these stars came together. It's hidden in the system's light curve. Observations clearly recorded the changes in brightness that occurred when each of the 3 stars passed in front of the others. But the resulting light curves don't match those of any known triple star system to date. The data that defines the system is so complex that no model so far has been able to perfectly reproduce its light curve. Astronomers prefer to describe this formation as a sign of things we haven't thought of yet. Another unusual feature of the impossible triple system is that it's not just physically odd, it's geometrically puzzling as well. The angular positions, mass distributions, and orbits of the 3 bodies appear to be in conflict with the conditions for dynamic stability. In other words, this system physically exists, but theoretically it shouldn't. This makes it a rare exception in astronomy. And just like other one-of-a-kind stellar cases, here too, we have observations, but no explanation. The light arrives, the data flows, but the meaning still hides in the distance.